Hi there and welcome back to chemistry. My name is Jeremy Krug, and in this video we're learning about some applications of nuclear energy and nuclear science. If you're new to my channel, welcome aboard. I hope you like what you see here. Check out the playlists, that's where the action is. And if you do like what you see and find that my videos are useful for your learning, then consider slamming that thumbs up button and subscribing to my channel. That way you won't miss a thing. This is the place for all things honors chemistry and AP chemistry. Well, jumping right into the first application of nuclear science, we're going to talk about nuclear fission and nuclear fusion and how those are different from each other. Now, nuclear fission is essentially defined as when a very heavy nucleus splits into more stable nuclei of smaller mass. Now, when I talk about a very heavy nucleus, generally speaking, I'm talking about those elements that are way down toward the very bottom of the periodic table. Things like uranium, atoms that have an atomic mass of 90 or higher, or somewhere pretty close to that. Probably the best example of nuclear fission is found in modern nuclear power plants. And so they'll have some sort of a heavy nucleus, some sort of a fissionable isotope there, and they're able to harness that energy in order to produce electricity. So nuclear power plants are a good application of nuclear fission. We also know that early nuclear weapons made use of nuclear fission as well. The first nuclear fission weapons were created back in the 1940s during the Manhattan Project, as you may have heard of in your history classes. Now, here is one of the ways, or one of the reactions in which nuclear fission can take place. We can have an atom of uranium-235, and it gets hit with a neutron. Now, as we learned earlier in this video series about nuclear science, you can't just take an atom of uranium or some other fissionable substance and expect it to split on its own. You have to do something to split that atom. It's kind of like if you have a window and you want to break that window, you can't just hope that the window is going to break spontaneously on its own. You have to throw a rock at it. And it's the same thing with these fissionable isotopes. You have to throw, in this case, neutrons at the uranium-235 atom to cause it to split. And when it does that, it undergoes fission. It breaks down into, in this case, two different isotopes. One of those is krypton-93. The other one, in this case, is barium-140. And notice what we get spit out on the end. We get 3 neutrons, and I don't have it written here, but we have a large amount of energy, and that's why someone would carry out nuclear fission to produce that energy, perhaps for nuclear power plants or something like that. So what we have here is we start with 1 neutron on the reactant side, and on the product we end up with 3 neutrons. Now, where do you think those neutrons are going to go? Well, they don't just go home and go to sleep. Those 3 neutrons are going to go back over here, and they're going to hit 3 other atoms of uranium-235. And the process is going to repeat. And it's going to spit out these other isotopes again. But this time, the second time around, you don't get 3 neutrons. Since we multiplied the recipe by 3, we get 9 neutrons the second time around. And even more energy. And guess where those 9 neutrons are going to go? Well, they're going to repeat the process, aren't they? And you'll have 9 neutrons that hit 9 atoms of uranium. And when the process repeats, we have even more energy, and the next time through, we get 27 neutrons. Do you see what's happening here? This reaction is just kind of growing on its own. This is called a chain reaction, where we have a process that starts, and it just kind of sustains itself. This is a self-sustaining chain reaction. And eventually, if you don't slow down these neutrons, it can go haywire, and if you don't slow them down, you can have something called a nuclear meltdown, and that's actually what happened at Chernobyl and at Fukushima, as you may have heard of in your history classes. So that can happen. In a nuclear power plant, they have control rods. And often these control rods are made of graphite, and their job is literally to slow down the neutrons so that you don't have a nuclear meltdown, so that those neutrons don't go haywire and get out of control. So here we have a good example of a chain reaction. This is what takes place in a nuclear power plant. Very safe if it's done correctly. Now, the other type of nuclear process that you need to know about is nuclear fusion. Now, if fission is splitting the atom, fusion is, putting atoms together. This is literally taking very small nuclei and combining them to form heavier, more stable nuclei. And so probably the best example of this would be what's taking place in the sun and stars. In fact, I'm going to go out on a limb here and say this is probably the most common process in the universe. Fusion is taking place in the sun, where hydrogen is being fused into helium, and in the process, unimaginably large amounts of energy are being given off in the process. So a very important process. Fusion is absolutely essential for us to live. That's what powers everything we do, basically. Hydrogen weapons, thermonuclear weapons, are another application of nuclear fusion. Those began to be produced around the 1950s. That is another example of nuclear fusion. Here's an example of the equation that is used in nuclear fusion, for example, in the sun, where we have multiple hydrogen atoms that literally fuse together at very, very high pressures and speeds, and we have a helium atom that's produced. And so the helium atom is produced along with a couple of positrons and then energy. And when I say energy, I'm talking about unimaginably large amounts of energy. So we have fission in nuclear power plants, fusion in the sun and stars. Now, what are some important uses of nuclear energy? Well, the first one that I want to point out to you is electricity. And for this, we're generally talking about nuclear fission. Now, in order to power a nuclear power plant, we're going to need some sort of fissionable material. Now, the most common fissionable material today, as of the time I'm recording this video, is uranium-235. And that is mined in different places throughout the Earth. Now, when you mine uranium-235 out of the ground, you can't just take those rocks and ship them off to a nuclear power plant and expect them to undergo fission and have a nuclear power plant from that. You have to prepare that uranium-235. One of the first things that they do is they extract the uranium from the ore that comes out of the ground, and they actually react it with fluorine to make a compound called uranium hexafluoride. It has the formula UF6. And then that UF6 is shipped off to an enrichment plant where that uranium is actually enriched to the point where it's about 4% uranium-235. Now, the reason I mention this is that if you just take uranium right out of the ground, uranium-235 is not a very common isotope in uranium ore. It's less than 1%, to be honest. And if you just take uranium out of the ground, you can't really do much with it. So what they do is they ship this to a plant where they basically remove some of the heavier isotopes from that uranium mixture there. That way they can have a much higher percent of uranium-235 in the sample. And if you have a sample where 4% or so of the uranium atoms are uranium-235, they can actually use that for fission in a nuclear power plant. It is a fairly complex process. They use centrifuges and things like that. I actually got a chance to tour a uranium enrichment plant several years ago. A very fascinating process. Uses a huge amount of energy in order to do that, by the way. Now, medicine is another very, very good use of nuclear energy. We use different radioactive isotopes. Perhaps you know someone who has had cancer and they have taken a radiation therapy. There are different radioactive isotopes that, when channeled into the right places in the human body, can kill cancer cells. And so a very effective use of radioactive isotopes. Also, diagnosis. Some of you may have had some sort of a diagnostic process, perhaps an MRI, and perhaps before that MRI, they ask you to drink some sort of disgusting milkshake, basically. And this disgusting drink basically has an isotope of barium in it. And when you drink that isotope of barium, it causes your digestive system to essentially glow under the MRI so they can see what's going on inside your digestive system. Now, that's an isotope that has a relatively short half-life, so it passes through your system. It's not going to hurt you, but it's very useful for diagnosing if someone has a certain disorder inside their body. So perhaps you've benefited from radioactive isotopes being used in medicine, or perhaps you know somebody who has. Now, a third use of nuclear energy is warfare. So fission or fusion nuclear weapons, these are products that have been produced over the last, almost a century now. And the hope, of course, is that those will never have to be used. But there are several countries that have developed these, and they use these as a deterrent in their defense systems. Now, a fourth use of nuclear energy that is really quite exciting is in scientific research. Now, as you take a look at the periodic table, you have probably seen that there are several elements down toward the bottom of the table that are man-made or synthetic elements. They're made in laboratories. Now, why would someone want to do this? Why would someone want to make new elements? Well, when we do this, we actually discover the fundamentals of the universe. Now, the way these new elements are made is they take somewhat smaller elements and they accelerate them to over 99% of the speed of light in something called a cyclotron. And then they literally smash them into each other, and the hope is that these little nuclei will fuse into each other and make a larger nucleus. And when we do this, it helps us to understand how nuclear fusion takes place in the sun and in stars. It helps us to understand how elements may have been formed in the opening moments of the universe. It helps us to understand the fundamentals of the periodic table and of our universe. So we have nuclear energy and four main applications of nuclear energy. So electricity, medicine, warfare, and scientific research. Now let's continue and talk a little bit about the effects of radiation for a few minutes. There are several different units that we use in science to calculate or to count how much radiation has been released or how much radiation someone's been exposed to. The unit I'm going to use in this video is the REM, R-E-M. That literally stands for radiation effect on man, as in mankind or humans. REM, REM. If you were somehow to be exposed to anywhere from 0 up to about 25 REM, you would not be able to tell immediately. You would not feel any immediate effect upon being exposed to that level of radiation. If we were to up the dose, though, from about 25 REM up to somewhere around 100 REM, you would probably notice a temporary decrease of white blood cells. Now, here's the thing about white blood cells. You aren't walking along and you all of a sudden say, hey, I think I'm having a decrease of white blood cells. You don't feel that necessarily. It's not something that you're going to necessarily feel immediately, but you probably know that white blood cells are important in your immune system. And so if you have a decrease in white blood cells, that means that you're going to be more susceptible to other infections, like getting sick, or perhaps a cold or some other sickness. So this is a level of radiation that absolutely could affect you. If we were to increase the dose from about 100 to 200 REM, now we're starting to talk about serious levels of radiation exposure. And notice the symptoms of this level of radiation. Someone would experience a loss of appetite. They would experience just a feeling of being weakness, being lethargic, this overall feeling ill or sick, diarrhea, a very intense headache. If they could eat food, they probably would not be able to keep it down. This is something we call acute radiation sickness. And this is a level of radiation exposure where someone would be getting really, really sick. Much beyond 200 REM, this is where we talk about someone losing their hair. Much beyond that, and it's very likely that someone would not survive that level of radiation, unfortunately. So these are effects of radiation from almost no immediate effect. I say no immediate effect because sometimes there are other effects on down the line, maybe months or even years later. Now, I do have a question for you. How many REM do you think the average person is exposed to in a typical year? So if you were to add up how much radiation you're exposed to just every day and add it up over a typical calendar year, how many REM would you be exposed to? Well, when I ask that question to my classes, some students say 100 REM or 1,000 REM. Some students say 10,000 REM. Some students say 1 million rem. Some students say on the low side, 15 rem. Well, as it turns out, you might be surprised that the average person is exposed to somewhere around 0.15 rem over the course of a typical year. Now, this may seem like a very small number. It is, in a way. The fact is that this number may be a little bit higher or a little bit lower depending upon where you live and depending upon your habits and your activities. In fact, if you look up this number online, you might find that some textbooks or some sources say that the average person is exposed to as much as 0.5 rem over the course of a year. And some people say it's as low as 0.1 rem. There are different values. And so I'm just using an average number here from all the sources that I was able to find online and in textbooks. Now, where is this radiation coming from? Well, you might be surprised. Over a third of this, about 35% of all the radiation exposure that you're exposed to comes from the sky. Cosmic rays, the sun, stars. That's a pretty good chunk of your radiation exposure. We can also say people. Now, you may not have realized this, but people are also radioactive. Somewhere around 18% of your average radiation exposure comes from other people. The carbon atoms in your body are undergoing beta emission all the time. There is a certain level of radiation exposure that you are exposed to just by the fact that you're around people. And that's a little hard to believe sometimes, but that's true. The Earth, there are lots of radioactive isotopes right inside the Earth. And so we can say that about 17% of your typical radiation exposure comes from the Earth itself. Now, if you were to add these three values together, 35% plus 18% plus 17%, you would get a total of about 70%. Now, what do these three things have in common? Well, they're basically natural sources of radiation, aren't they? These are what we sometimes call background radiation. This 70%, this is an amount of radiation that it's very difficult to avoid. You can't really get yourself away from the Earth, can you? You could become a hermit and live in a cave and perhaps get away from people, or perhaps you could get away from the sun a little bit and stars, but we're all exposed to the Earth. It's very difficult to get away from all of this level of radiation. So a lot of this radiation you're going to be exposed to no matter what you do. Now, the next several sources are what we might call artificial sources, man-made sources of radiation. For example, medical and dental x-rays. Most people have about 20% of their annual radiation exposure comes from medical and dental x-rays. And this may seem like a lot, and at some level it is, especially considering the fact that most people only get a couple of these a year. Now, some people might go an entire year without getting an x-ray. So that means that their value here would probably be lower than 20%. And some people are always in the doctor's office getting x-rays, so maybe their value would be higher. Air travel. Now, air travel has to do with the fact that whenever you're flying, you are a little bit higher up in the Earth's atmosphere, and so you are exposed to more sun, stars, cosmic ray radiation. So that's a little bit higher. If you're a frequent flyer, it could be lower than that if you don't fly at all. So about 5%. Nuclear waste and weapons. About 4% of the average person's radiation exposure comes from that. And of course, depending upon where you live, that number may be a little bit higher, that number may be a little bit lower. If you add all these numbers together, that gets you pretty close to 100%. Now, you might notice that there are some things on here that are not listed, that are not sources of ionizing radiation. What sources might be missing from this that maybe you thought would have been on the list? Well, how about microwave ovens? Microwave ovens are not significant sources of ionizing radiation. Some people were told when they were younger, don't stand in front of the microwave, you'll get radiation, whatever that means, get radiation. Well, microwave ovens are not sources or not significant sources of ionizing radiation. And you can test this with a radiation detector, a Geiger counter. And I will tell you this, if you do have a microwave oven that is belching out ionizing radiation, you need to get rid of that thing. It's not something that you want to cook your food with. Also, television. I know some people have been concerned that television gives off, gamma rays or something like that. That's not the case. Watching TV is not going to be a significant source of ionizing radiation. Hey, hope you learned something from this video. Hope you found it useful. If you did, please consider slamming that thumbs up button. I would really appreciate that. Thank you for watching this video, and hope to see you in the next video where we can learn some more chemistry together.